Alright, so in this video, we're going to do more Pythagorean theorem. Pythagorean theorem. Again, I don't think it should be named this. Considering Babylonians found it, and it was well known by many people way before the Pythagoreans, so name it after that group of people. I don't know. But anyway. So where we left off, so we did dissection proofs. We're going to use another proof via similar triangles. We'll talk about it in just a second. So this is our triangle. Let's label long side B, short side A, and hypotenuse as always. By the way, hypotenuse just means it's across from the right angle. You can see that's just directly across. C does not have a right angle next to it. That's how you know it's C. Wait, let's keep going here. So, we have the triangle. Here's what we're going to do to it. We're going to drop a line down. This feels familiar, but it shouldn't be. I mean, it is, but it should be, but it also shouldn't be because we're doing something different with it. And here, by doing that, we cut the side into two parts. So let's name those two parts. Let's label this side, I don't know, L, M, what's another letter? N. Letter? What? Alright, so what we know about those, we know that L plus M equals C. And then you could use Pythagorean theorem to talk about N, M, and B, but no, whenever you're doing a proof, you never restate yourself, for the same reason that if you define a word like theorem, you don't say, okay, a theorem is part of a theory that does this. No, that's ridiculous. You don't do that. Either way, let's keep going here. So we have this triangle. What do we know about it? Alright, let's label some angles. Let's call this theta. Let's call this guy. And I keep using theta and phi. Yeah, let's just keep doing it. More phi, more theta. Alright, so what do we know? If you take the smaller triangle, it has an angle here of theta and a right angle. Alright, and also side of L, also side of M, no, N, my bad. It's an N right there. And the side of A. Alright, let's draw out the other triangle here. By the way, this proof was done by, oh man, I'm going to say this wrong. It's like Baksara. I believe it's spelled like this. Either way, one of the most famous Hindu mathematicians. This was like after Pythagoreans, but it's also before like standard, like way before calculus and stuff like that. Let's label these sides. That's N, that's M, that's B. Alright? So, if you notice, this has a side of phi and a right angle. Alright, let's also make a note. Our big triangle here has a right angle, a theta, and a phi. So if we have a right angle and a theta, our other angle should be phi, no matter what. So if our other angle is phi, then the first angle was theta. So check it out. All of these triangles are called, all of these are called similar. And similar just means that, well, they literally are similar. All of these triangles look relatively the same. If you turn it from a different angle, I guess it'd look like that. Alright, you can see they all kind of have a very similar shape, and they really should. There's no reason they shouldn't. So let's keep going here. So L plus M equals C, whatever. That's just a fact that we stated by drawing that out. Alright, so here's what we can do. Without even using trigonometry, we can just say that all these ratios are the same, if they're the same relative to each other. So let's look at this big triangle. Let's do all our ratios relative to the hypotenuse. The hypotenuse here is A, hypotenuse here is C, hypotenuse here is B. Alright, B divided by, let's say, M. What does that equal to? Well, M is the side next to the phi, right? The side next to the phi, that is not the hypotenuse. So in this case, B divided by M here, what's the hypotenuse here? That's C, that's always on bottom. Why did darn it, I want hypotenuse on bottom. you'll see that helps us with the math a little bit. So m over b. All right, good. And that looks bad. Let's just rewrite it. So we're taking hypotenuse and taking the side next to the phi. So that is b over m. No, m over b. Wow. And that's going to be equal to the same ratio of these guys if we take the same side lengths. So c in this case is b, right? It's the hypotenuse. And b in this case is the side next to the phi. All right, and let's do the same thing with this guy, just with different sides. A is the hypotenuse here, and A is also the side length here. So let's use the relative sides that use A in both of them, if that makes sense. So if you notice, A divided by C, that is going to be, A is the hypotenuse here, so we're dividing by the hypotenuse. So it's also going to be the side next to theta, L in this case, multiplied by, divided by the hypotenuse. So there's L divided by the hypotenuse, side next to theta. This is A divided by the hypotenuse. That is the side next to theta. All right, we're good. So we have these two relationships here of this fraction. So here's what we're going to do. We're going to multiply out the fractions. All right, so let's multiply both sides times A, because this times A, then there's no fraction anymore. This times A is A squared. Now we also have to multiply out the c, so multiply both sides by c. The c goes away on this side, and the c goes to this side. So c times L. All right, and now let's take this fact here. Multiply this side times c, so you get c times m. Centimeters, nope, that's not what it means. And b times b, that is b squared. All right, and now we're going to use a simple fact that you can add any two equations together. Like if you had 2 equals b, and a equals 4. Then a plus b, combining those equations, you have a plus b equals 6, right? That should make sense because b is 2 and a is 4. So we're going to use that same fact. Ignore the fact that I reused a and b. That means nothing here. Man, let's do it. There you go. Now you can see it. Ha. All right. So we're just going to add these equations together. So we get c L plus c m equals a squared plus b squared. And now you're stopping thinking, no, this didn't help us. I don't see a squared plus b squared equals c squared. There's something different. Except, here's what we're going to do. This has a c in it. This has a c in it. Let's factor it out. That's c times L, and that's c times m. All right, and that equals a squared plus b squared. Do you see a factor we can use on this page? Because you should. L plus m is equal to c. So replace that with c. All right, c times c is c squared. Therefore, a squared plus b squared equals c squared. That is a proof using similar triangles. All right, because these are all the same kind of ratios. I don't know, I'm coloring it now. Whatever. So that was a proof by box. Sorry, there's another one that's another kind of dissection. I'm just going to skip with that. So now, let's go on to something a little more complicated. All right. So you know cosine plus sine, right? Cosine squared plus sine squared. So using this one fact, we'll prove the Pythagorean theorem yet again. Cosine squared plus sine squared equals 1. And how can you know that's 1? Because just starting with that fact, I feel like we're already cheating. Well, it kind of is, except for cosine looks like this. We're going to do this visually. All right. So those are axes. So cosine looks like this. Let's do it in orange. All right. Cosine starts at 1. Goes dips between. All right. And now let's make the other one in green. So sine. All right. Starts at 0 and oscillates from there. And just need to make sure I do this right. It's about that. Now here's the thing. If you just add these two values together, at this point, it would be a value of 1. At this point, it would be a value of 0.5 here, and this would be I don't know, something not 0.5. Either way, it definitely wouldn't add up to 1 at every point. If you look here and combine that with this distance, you're going to get something like this distance because you have a negative distance. And so you'd get some weird other shape if you start adding these together. And then you get the highest point here, and start getting lower again. Just adding these together. And so you should see definitely that this wouldn't work out very well. We wouldn't get anything very awesome. However, that's only if you add them. This is talking about squaring it. So let's talk about these curves squared. So let's use more axes, except for we're going to draw these squared. So the top point here is 1. All right. Well, I should draw it right here. So 1 squared is 1. Here is 0. 0 squared is 0. Negative 1 squared is positive 1. Then 0. Right? We're talking about orange here. Then that's positive 1 again. 0, positive 1 because negative 1 times negative 1, and positive 1. Then this would be 0, positive 1. Alright? And I'll tell you right now, if you square a number less than 1, it's going to get smaller, no matter what it is. So a number very close to 1, it's just going to become closer to 1. Stuff like that. So this is going to have a very sharp curve. Alright? It's going to be something like this. Alright, I'd prove this, but I think you get the idea. Alright, it's going to have this kind of shape. Very similar to the actual shape of cosine, except for that's always positive, notice that. And now, let's take the other curve, green. Guess what, if you did the same thing, it's the exact same thing happening, except for with the other point. So 1 times 1, negative 1 times... am I doing this right? Right there, it should be 0. There you go. I guess I should be passing through there. Alright, and it's going to make those shapes. And now what do you notice? If we added up those values together at every point, let's do it in purple. This value plus this value is 1. This value plus this value, it shouldn't be as steep. It should be half plus another half. I drew that very poorly, but whatever. The value here should be 1. The value here, this is supposed to be closer to top. See, I drew orange a little poorly, but whatever. So combining that with the small distance right here, and you get a positive distance of 1. 1, 1, 1. You can try this for yourself. Actually graph it on something or more trustworthy than just me. But check it out. You always get 1 if you add those two values together. It's starting to look like a DNA or something. It's always 1. And that's if you add them together. So now that checks out. And so how are we going to use that? So let's draw a triangle. Label a theta. Let's call this theta. Let's call this B. Let's call this A. Let's call this C. All right. Cosine of theta, it's always the x one if theta is right here. So it's A over C. And sine of theta is B over C. It's the exact opposite ratio. And so using this fact right here, this says that cosine squared is this squared, right? These squared are just this squared. That's A squared over C squared. Then we're going to add that to this squared, sine. Sine is B squared over C squared. And now what is that equal to? It's still equal to 1. Now let's multiply everything here by C squared. Pretend it's like a 2 or something. Let's get rid of it. So multiply everything here by C squared and everything here by C squared. And the C squareds go away here. Yep, that's just a fraction going away. And that's just a fraction go away. So A squared plus B squared equals 1 times C squared is C squared. We're right on so many levels. It's undisputable. And I still have time in this video, so I'm going to talk about the Pythagorean theorem and what it tells us. So now we're done with proofs for now. You can probably find a ton more out there, and sometimes they get more complicated, like you can do it with differentials. I would have done that, but I don't feel like doing calculus right now. I feel like doing more geometry-based stuff. But just know that can be done. And differentials are just using those tiny dx's and those tiny dy's. See what happens when you mess with them together. You can integrate them, take derivatives, whatever. But that's just a way to prove it. You can look this stuff up. I actually recommend Wikipedia for this. I don't usually recommend Wikipedia for math, but it's definitely right. It's a cool way to do it. But what does a squared plus b squared tell us? If we have a distance, this is very helpful for standard graphing system. If you have a distance here, let's mark it in purple. And then you go distance up. That's how you label points, right? You'd have an x distance here and a y distance here. The distance right here, whatever this y value is and whatever this x value is, using this fact, in this case, a squared or b squared, either one, is x squared. And b squared or a squared is y squared. That is equal to what? That is equal to c squared. So let's call this r. I like calling it r, like a radius. You get r squared. All right. So now, here's what we're going to do. We're going to square root both sides. Right? The square root would get rid of it. Now, normally you have to do plus or minus, but if you don't do plus or minus, you get square root of x squared plus y squared equals r. That's assuming that our result here is positive, which it is visually. So when can this be useful? Well, this is what we call the magnitude of r, if r is a vector. All right, that doesn't make sense right now, but it will in... So a vector is just a way to talk about points in a different kind of way. So if you go back 2 and up 3, all right, that's it. That's what you call your y component, is your y distance here, and no x distance here. All right. And then you make an arrow here. And the arrow is pointing away from the center. All right, it's always connected to the center, in this case. And if you did coordinates, you'd be like, oh, that's -2, 3. 3 is your y, -2 is your x. But the other thing you can do is, let's call this r first. Let's call it p, because we already used r. And then we put an arrow over it. I don't know, usually cut off the arrow. You don't have to. You'd either make a full arrow or cut it off. I think it looks cooler if it's cut off. And you'd say that p, arrow, is equal to, it's a -2, right? And we say that's an I component, all right? And we put a hat on it. Because I corresponds to x and y, all right? So that means go -2 in the I direction. I represents this x direction. And 3 represents your y direction. And guess what? If I is x, what's after I in the alphabet? J. So we do a curly little J with a hat on it. And even cooler, if you have another direction, like in 3 dimensions, just bring this line out, you could represent a vector in 3 dimensions by just adding a k. And whatever that k value is. In this case, it's 0 because it's not going out that way or else. And even cooler, we can't even visualize 4 dimensions, but if we could, and we know a value at 4 dimensions, what's after k? L. So we have an L vector. Then you could keep on going here, or M vector and stuff like that. It just gets crazy. But this system is really useful for talking about things with a ton of variables, because you have so many different directions. And if you think, okay, so what? What does this have to do with Pythagorean theorem? You just wasted my time here. Well, I kind of did, but it's also useful because know what the magnitude of this vector is, and magnitude tells you the length. Or if, let's say this was your speed in both directions, so you go -2 miles per hour and 3 miles per hour here, the magnitude is always going to tell you the component, all right, in the direction that the vector is going in. It's called a vector, by the way. Kept saying vector, but I didn't spell it out. All right. So what this means is that using this formula, what's the x component? That is right here, and there's your y component. Ignoring all this stuff, just saying that it extends well into more dimensions. So exponent, that's -2 squared. That's just going to be +4. And then that's y squared. That is, in this case, 3. 3 squared is 9. Square root of 4 plus 9. 4 plus 9 is 13. So the value here is square root of 13. And that is what magnitude tells you. And you'd write it like this. You'd put a double bar, because magnitude is just a number. It doesn't tell you anything about directions. Notice how I didn't write I or J in any of these. But this is a very high math concept, but it's really just talking about these as an actual x direction and an actual y direction instead of talking about them as coordinates. All right. And this magnitude concept also shows up in imaginary numbers, which we'll cover more later. But if you have imaginary direction up here and a what's it called? Real direction here. So if you can represent any complex number. So if this was 2 in this direction, this was 2 in this direction, this complex number would be 2 plus 2i. 2 in the imaginary numbers and 2 in the real numbers. Very similar to this, interesting enough. But the magnitude is just this number squared plus this number squared. 2 squared is 4. 2 squared is 4. So we get 4 plus 4, that's 8. Square root of 8 is the magnitude. So if you're talking about the magnitude of a complex number, which sounds like a very complicated concept, it is just the two numbers squared, the two components squared, square the whole thing. And that's really it. I don't want to make it sound easy, but in a sense it really is. And, man, should I just use the rest of the video? Yep, we're going to do more. Let's talk a little more about vectors for a second. Just because we're on the topic of Pythagorean theorem. And Pythagorean theorem shows up all the time. In fact, we used it in order to prove some integral rules. So it's not like a simple geometry rule and that's just it. No, it extends super well into other problems. So a squared plus b squared equals c squared. All right. So interesting enough, writing it in the form square root, let's use the r. All right. This time I'm not going to put double bars or anything. X squared plus y squared. Interesting enough, if you're in one dimension, what is it? You just remove your y component. And if you think, oh no, that simplifies easily to x, well, you're wrong. That actually simplifies to the absolute value of x. Because if we put negative 2 here, square it, you get positive 4. And then if you square root both of these, you square this, then square root of 4 is positive 2. And so that washed off the negative. So whenever you talk about absolute values, that is the absolute value. And in another word, that is the magnitude of a point. Have you ever learned absolute value as on a number line? Right? It's the distance from the origin, the center. So if you go negative 2 in this direction, or you go positive 2 in this direction, guess what? The distance here is still 2, and the distance here is still 2. However you measure it, the actual literal distance here, even though it's negative direction, is a positive 2. And that is represented by Pythagorean theorem. I call it the Pythagorean theorem in one variable. And that's one dimension. That's just a line. Now, if we're in 2 dimensions, yes, it just becomes the Pythagorean theorem like this. If you notice, it's always positive because you're squaring numbers and square rooting. Unless you use imaginary numbers, but we're not getting into that. Now, guess what? The theorem is in 3 dimensions, and we're going to call the third dimension z, because x, y, z. Well, guess what? The Pythagorean theorem states if you have an x component and a y component and a z component, you just square them all and square root the whole thing. Done. And guess what? 4 dimensions. X, y, z. Let's call the next one omega. I don't really care. Let's just say omega is your 4th dimension component, all right? And check it out. That's also the magnitude in 4 dimensions. That's how easy it is. And you can verify this by, if you have something in 3 dimensions, you kind of have a distance here, you have a distance here, and then you have a outward distance here and outward distance here. Let's call this k for a second. Let's call this guy, this is your z. Well, no, this is your y because it's your height. This is your z because it's the outward component. This is your x. And so the length of k right here, or kappa, I guess, is equal to square root of x squared plus z squared. But k is not what we want. We want this length of r, all right? So r right here is equal to this length here. There's a right angle right here. Squared plus this length squared, which is So this squared is x squared plus z squared. That gets rid of the square if you square that. And this length here is y squared. Rearrange it. And yes, it checks out. It is this exact formula. And so Pythagorean theorem, I haven't even begun to tell you how applicable it is. But I introduced vectors just to talk about this amazing concept that is the Pythagorean theorem. And last but not least, no, I don't need to talk about it much more. I think get it. Magnitude, that is a very important concept. How much power is in an object or anything of that sort. If you have two components, you can just combine it with the Pythagorean theorem. Alright, we're done here.